Let's crack management exams. Join Unacademy, India's largest learning platform, and get the best possible resources to crack the CAT, the GMAT, and all other management exams that you're aspiring for. My name is Anand Venkatesan, and I'm an educator with Unacademy. Here's a brief look at my profile. As you can see, I've done my engineering from VIT Vellore and then did my postgrad from IIM Bangalore. I have about a decade's worth of experience in having trained students for a variety of these management exams that include, colleges such as the IIMs, ISB, SPJ and XLRI, Snapchat, and many other exams. Right, so that was a brief look at my introduction. Here's a quick look at what Unacademy offers to you. Well, I think it's one of the best platforms to learn, online. And here's why. Well, you get everything that you need to prepare, which means you get classes which happen live on a daily basis, right? Which means, well, not every batch is going to be a daily batch, but you can choose multiple batches when you register, and that means that your preparation can actually be live and on a daily basis. As regards tests and quizzes, there's plenty of content that gets created and shared on the platform. You can take tests, you can analyze your performance, but I think the biggest seller is that you get structure to your preparation, because once you join a batch, there is a regular schedule of classes that happen, which means your preparation sort of falls into a very rigid schedule. And most important is the fact that all the material that you access on Unacademy's platform is unlimited, which means that there is no upper limit on how many educators you can learn from, how many batches you can join, how many tests you can take. Everything is unlimited. Here are the kind of educators who will be available on the platform for you to interact with. You can see these are subject matter experts, people who scored 99 percentile many times in the past few years. These are people who have trained students for thousands of minutes on the platform. Though these are people who understand what exactly goes into teaching you the concepts online. Live classes happen in two modes. There is one called special classes, which is more, think about these as trial classes, because they are free of cost, right? The idea is to experience the platform before you register, and when you register to access Plus, right? And Plus gives you access to multiple batches, right? Once you are on Plus, you can access multiple batches, each of which will have many of these sessions. So the biggest advantage is that once you upgrade to Plus, you get access to many more live classes. B, you get access to such batches that created on almost a weekly basis. Batches that target different things. They can target CAT, they can target the ZAT. There are batches right now which are targeting next year's CAT. Batches that target specific areas that you can do extra preparation, like parajumbles or reading comprehension. Basically everything that you need to sort of fine tune and keep a sharp focus on various test areas. All you need to do is register to one of these subscription plans. I think two recommendations I have here. One, use my referral code for a 10% discount, and secondly, choose as long a term as you can possibly go ahead with, because access not just tests, access classes, access all the resources for longer duration if possible. Alright, with that introduction, let's take a deep dive into today's session. Yesterday we introduced number properties for specifically the GMAT exam, and today we'll take that discussion forward, look at a few more sort of question types and concept areas within number properties. We start with, this is the agenda. We basically will focus on factors and multiples today, and obviously their applications in HCF and LCM. Look at the kind of problems you can get revolving around HCF and LCM, but then also understand how to count factors and multiples around a particular given number. So probably the latter part of the session, where we deal with factors and multiples, is going to be slightly more advanced. Here's where you sort of start getting into tougher areas, right? Tougher areas, which basically means that these will be mostly 700 plus level of questions. So if any time you face these questions, tell yourself you're doing well. Right, start with LCM and HCF. Exactly what is the least common multiple? Well, smallest number. Remember, the key word here is that you're looking for a common multiple. I think the two big words here, you are looking for a multiple, right? That is common to all numbers, right? Now, what do I mean by a multiple? A multiple is number that can be divided by that given number. Like for example, if I want a multiple of 5, I want a number that can be divided by 5. It will be like 5x, 5 into 2, 5 into 3, 5 into 5, etc. So when you are talking about the least common multiple, you want one number which falls in the table of 2 or 3 given numbers. Well, how do you calculate LCM? Well, I'm sure you've done this at, in school or in college. Express, basically prime factorize all numbers. Then consider an example, 20 and 48. So you can write 20 as 2 square into 5. You can write 48 as 2 power 4 into 3. Right? Once you do this, you look at every single prime factor. Right? Least common multiple will include all the factors, and for every factor between the occurrences in number 1 and number 2, you choose the higher value. So for example, 2 occurs twice in 20 but occurs 4 times in 48, which means you should choose 2 to the power 4. 3 and 5 occur once each in the two numbers, so include them once, and so the LCM will be 16 into 3 into 5, that's 240. So the LCM of these two numbers would be 240. You can get that by prime factorization. Okay, so two things to remember. One, I'll calculate the LCM when I want one number which can be divided by each of these bigger numbers. Usually that number will be larger, but I don't think that's the, I mean, even though it says least, you're getting a number which is bigger than the two numbers, right? That's a hint. And obviously you should know how to calculate it. What is HCF and when do I use it? Again, the key word here is common factor, right? This is a common factor. So what exactly is a factor? A factor is a number which can divide the given number. So if I say give me a factor of 10, that's going to be 2, 5, 1 or 10 itself. So any number which can divide that number will be a factor. So if you have one number which can divide two or more numbers, it's called a common factor, right? And the biggest such value will be called the highest common factor, right? So HCF essentially denotes the largest number that can divide all the given numbers, whereas LCM denotes the smallest number which can be divided by the given numbers, right? How do we go ahead and calculate this? Well, again, prime factorize all the numbers, 20 and 48. We've seen we can prime factorize it this way, but when calculating the HCF, you only choose those primes which are common, right? In this case, the only prime that is common to both these numbers is the prime factor 2. And so when you get the common, occurrence, then you choose its minimum number of occurrences across all given numbers. So in this case, 2 occurs twice in both places, so that's what you will choose. So LCM will be 2 square or 4, right? And that's a method for calculating the HCF. I hope you also remember the long division method, whereby you can divide the larger number by the smaller number. 20 into 2 is 40, right? And when you get a remainder, you divide the previous divisor by the remainder. 8 2s are 16, that's a remainder of 4. Now bring the divisor down again, that becomes 8. 4 2s are 8, and the stage at which the remainder becomes 0, the divisor at that stage is the HCF, right? So long division method as well as the prime factorization method. But no doubt you should know how to calculate, but more importantly, when do I need to calculate? If you want a number which is smaller than given numbers and can divide it, you want HCF. If you want a number which is bigger than the given numbers and should be able to get divided by them, calculate the LCM. Alright, so let's look at a few properties and applications of these concepts. One most useful property, some very pretty basic one of that, is that for two numbers A and B, the product of the numbers will be equal to the product of their LCM and HCF. So for example, 20 and 48, we saw that the LCM was 240 and HCF was 4. If you multiply that, you'll get 960, just as you'll get 960 when you multiply 20 and 48. Okay. Second sort of trick to remember, or second sort of point to notice, is that since HCF is a common factor, if you know the HCF, you can assume the numbers to be multiples of the HCF. So if I know two numbers have HCF as 6, then I'll assume the numbers to be 6A and 6B. Or for example here, if I have the HCF of two numbers as 8, then the numbers themselves will be 8A and 8B. But A and B must not have any factor in common, right? Because you've already gotten 8 as a common factor, you shouldn't get anything common between A and B, which means A and B must be co-prime. That's the definition for such numbers, right? Numbers which don't have a common factor, numbers whose HCF is equal to 1, right? And the third property is that when you're dealing with fractions, LCM of fractions would be LCM of the numerators upon HCF of denominators. And likewise, here's an example to illustrate this point. LCM of 2 by 3 and 3 by 20, right? LCM numerator 6, HCF of denominators 4, so 5. So required LCM will be 6 upon 5. Similarly, if you want HCF of fractions, then calculate the HCF of the numerators and divide that by LCM of denominators. Consider same example, 2 by 5 and 3 by 20. HCF of the numerators is 1 and LCM of the denominators is 20. So the HCF of these two numbers would be 1 by 20. Okay, now that we know the basic properties, let's also look at a few abstract applications of LCM HCF. Obviously, there are the basic level of questions which will directly test whether you understand when to use LCM, when to use HCF. But then there are some other pointed sort of applications. So, for example, if you want a number such that it leaves the least number that gives the same remainder when divided by divisors A, X, Y and Z, right? So, if you take a number and when you divide that number by X or Y or Z, you get the remainder as A in all cases, then such a number, it can take any, there are many infinite such numbers that are possible, but the smallest such number would be the LCM of X, Y and Z plus the common remainder A. Yeah? So LCM plus A, and if you want other numbers, you take the LCM and multiply it with another integer, right? LCM into 2 plus A, or LCM into 3 plus A, or LCM into 4 plus A, right? So you can generate all such numbers where the remainder remains a constant. So consider this example. Supposing I want the least multiple of 7, which when divided by 6, 9, 15 and 18 gives a remainder of 4. Right? Now I will ignore the first part of the statement. Forget that it's a multiple of 7. You want a number which when divided by A, B, C and D gives the remainder as 4. Right? And you also want that number to be a multiple of 7. So first and foremost, you'll say, for these 4 numbers, you'll calculate their LCM. 6, 9, 15 and 18, calculate LCM. How do I calculate the LCM? Let me illustrate this point. You can also calculate LCM in pairs. LCM of these two numbers is 18. Think about just a table of 6. 6 2s are 12, 6 3s are 18, and there you go, 18 is divisible by 9. Similarly, with these two numbers, I could do the same thing. Talk about the table for 15. 15 into 6 is 90. 18 into 5 is also 90. And obviously, 18 and 90 will have LCM as 90 itself. Right, which means I can calculate LCM of these 4 divisors as 90. So then all numbers of the form, 90 into something. 90 is the number which is completely divisible by each of these divisors, which means if you want the remainder of as 4, then it will either be 90 plus 4 or a multiple of 90 plus 4. Right, 90 into 2 plus 4, 90 into 3 plus 4. And you want the smallest such multiple of 4, right? So hit and trial time, right? You put K as 1 and you'll get 94. Is it divisible by 7? No, it isn't. Then you put K as 2, right? You put K as 2 and you'll see 180 plus 4, 184. Is that divisible by 7? No, it isn't, right? And you keep trying and you'll eventually get 90 into 4, 360. 360 plus 4 is 364. And 364 indeed is divisible by 7, right? So 364 is the smallest number which gives a common remainder with these 4 divisors but is divisible by 7. Right? So I hope it gave you a flavor of the kind of question that you can get, right? It should be steeped in common remainder, then you can use this concept. Another application is, what if you have divisors which are what if by dividing by A, X, Y and Z, well, in the previous case we got the same remainder A. In this case, what you'll get is the remainders are equidistant from the divisors themselves, right? Which means if the remainders are X minus A, Y minus A, Z minus A, then the difference of divisor and the remainder for every number will be A. Right? Sounds complicated, right? Well, not so complicated actually, right? Consider an example. You want the least number which when divided by 20, 25, 35 and 40. 4 divisors, and you want the remainders to be 14, 19, 29 and 34, right? So how do you notice this pattern? Look at 20 minus 14, 6. What is 25 minus 19? Also 6. What is 35 minus 29? Also 6. 40 minus 34? Also 6. So all the remainders are equidistant from divisors. So what do? You basically take the LCM of all the divisors and you subtract this distance from it, right? Everything is 6 away from the divisor. So what you can do is calculate the LCM of, once you notice the pattern, calculate the LCM of these divisors and subtract 4 from it. LCM of divisors, again, again you can approach this in pairs. 20 and 25 will have LCM as 10. 35 and 40. 35 and 4. 35 and, this is 5 into 8. This is 5 into 7, right? So 5 is common in the LCM. 7 and 8 will also come. So you'll end up getting 35 into 8, that's 280. Right? And then if you look at 100 and 280, then you'll see LCM will be 1400, right? Which is 5 times 280. So the moment I get LCM as 1400, subtract 6 from it, that will be the smallest such number which is divisible by all of the 4 divisors, which when divided by the 4 divisors gives these remainders, right? Any questions, any doubts up until this point? Right, if there isn't any, let's look at some problems, practice questions. First question, you want the length of the largest square tile which can be used to pave a square of dimensions 221 by 391. Right? Largest square tile that can be used. Right? Clearly, the tile should have a integral length. The implication is that the tile will have an integer length. What will that length be? Just give me a second. Do you have an answer for me, Shaurya? Right. So the idea is that you're looking at, the length and the breadth. Right, so if you want a tile to fit in here, right, what you're saying is that you should have an integer number of square tiles, right? So this length of 221 and this breadth of 391 should both contain an integer number of tiles, right? Let's say the length is L, so 221 should be a multiple of L and 391 should also be a multiple of L, which means L is a common factor. Right? And if you want the common factor, and the question also says find the length of the largest square tile. So largest square tile means you want the L to be large, right? So you want highest such common factor, and HCF of these two numbers, 221 is in fact 17 into 13 and 391 is 17 into 23. So clearly HCF will be 17 feet. All right. Let's move ahead. Here's question number 2. Oops. Yeah, question number 2. At the bottom of your screen, 3 nylon cords. Alright, let's look at this. 3 nylon cords are divided into short portions of equal length. Right, so each of these is divided into equal length, portions of equal length. Let's say that length is x. So this one will be 28 will be x into A, 42 will be x into B, and 112 will be x into C. So what is x? It's a factor of these 3 numbers. So you want a factor of these 3 numbers. A common factor will be the length of those portions, and you want the length of the portions to be maximum, right? So you want the common factor to be maximum. So HCF is what you want to calculate. In this case, 14, is the HCF, which will be the value of x, right? How many portions will the third chord be divided into, right? 112 is indeed equal to, 14 into 8. So my answer, 8 portions. Alright, good job. Moving ahead. Here's question number 3. One p.m. Okay, right? So 3 alarms go off every 5 minutes, 12 minutes, and 45 minutes, right? Which means if the first alarm goes off every 5 minutes, it's going to go off at 5, 10, 15, 20, 25, right? So at multiples of 5. This is the first one. So second one would be at a multiples of 12, and third one would be multiples of 45. And you want all 3 of them to go off simultaneously, right? And the last time they went off together was at 10, right? So let's calculate the common multiple. LCM will be the earliest, time that you need so that they ring again, right? LCM of 5, 12 and 45. Let's work in pairs. 5 and 12 have an LCM of 60, right? So you want LCM of 60 and 45. 45 is 15 into 3 and 60 is 15 into 4, right? So you already have 15 in common, and 4 and 3 will have an LCM of 12. So LCM of these 3 numbers will be 180. So it will take 180 minutes for them to ring again, right? That means it will take 3 hours for them to go off again. So if they went off together at 10 a.m., they will again ring at 1 p.m. Good answer. Alright, here's question number 4 showing up on your screen now. Alright, let's look at this. So it says the HCF of two numbers is 6 and we are given that their sum is 48. So if the HCF of two numbers is given, you can assume the numbers to be 6a and 6b. And since their sum is given, you should say 6a plus 6b should be 48. But remember, if you assume the numbers to be 6a and 6b, then a and b must be co-prime. Right? Just keep that at the back of your mind. Which means I'll get a plus b as 48 upon 6, that's 8. So how many integer values can you get like this, right? So 1 and 7, yes, co-prime. 2 and 6, no, not co-prime. 3 and 5, yes, co-prime. 4 and 4, no, not co-prime. Right? So how many such pairs are possible? Answer is 2 such pairs are possible. Yeah, I can see you've corrected yourself. Right? Because if it says how many pairs, it clearly means unordered pairs. Alright, here's the next question. Question number 5. See if you can figure this out, Shaurya. Right, so think about it, right? These are people who are running around a circle and given their lap times, which means A will get to the starting point if they start from here, X, right? A will come back to X after he runs one full lap, right? Which means he comes there at 24 seconds, then again at another 24 seconds later, that's 48 seconds, and another 24 seconds later, that's 72, and so on. What are these? Multiples of lap time, right? So A will get there at a multiple of 24, B will get there at a multiple of 36, C gets there at a multiple of 48. And since you want them to meet at the starting point, you want LCM of when all of them get there, LCM of their lap times, 24, 36 and 48. So between 24 and 48, LCM is 48. And between 36 and 48, remember this is 12 into 3, this is 12 into 4. So you've already found 12 in common, right? So calculate the LCM of the remaining two numbers, 3 and 4 have LCM as 12 again, right? So you'll get 144 seconds as the LCM. So the earliest they'd meet is after 144 seconds, and that meeting will happen at the starting point. Right, here's question number 6. I know it's written at the bottom of your screen. See if you can figure this out. 6.23. Okay. Total number of, minimum number of rooms needed, right? So what you want is students to be seated in rooms so that each room contains or seats an equal number of students, right? And all students in a room belong to the same section, right? Let's say you seat n students in a classroom. All these n students will be from one classroom. So n plus n plus n at some point will become 90, which means you need A classrooms for this section. N into B should then be 120 and n into C would then equal 135. So what is n? A common factor. And since you want to minimize the number of rooms, you'll have to seat as many possible numbers of students as possible. So you want n to be as large as possible, as high as possible. So you want the HCF, and HCF of these numbers at a glance itself you can figure it out. This is 15 into 6, this is 15 into 8, and this is 15 into 9, right? Which means that the HCF is 15, right? And how many classes do you need? 6 plus 8, 14, 14 plus 9 is 23. So total minimum number of rooms needed will be 23, right? By choosing some other value of n, you might still satisfy this condition, but you need more than 23 rooms for sure. Alright, here's another one. How many times will you need the function h, which is nothing but the GCF or HCF? How many times will you need to apply the HCF function if you want HCF of all numbers in the set of n positive integers? Option B, n minus 1 times. Well, easy to verify, right? What if I have, let's say I have 3 numbers. Let's consider 4, maybe 6 numbers, right? So if you have 4 numbers, what will you do? A, B, C, D, right? You could pair them. So apply HCF once, apply HCF once. So H1, I'll get H2, and then you will apply HCF of these 2 numbers, that's H3. That's your final answer. How many times did I do it? Once, twice, and thrice. So with 4 numbers, you need to apply it 3 times. How about 6 numbers, right? So A, B, C, D, E, F, right? Once, twice, thrice, I'll get H1, H2, H3, right? So 3 times done. 4th time, that gives me H4, and then 5th time. So there you go, 5 times. So if you have n numbers, you seem to be getting n minus 1 times. It cannot be n by 2 because that won't work for 6. It won't be n because that doesn't work for either. And it seems like it will be n minus 1. Right? You can even derive this in generic terms, by the way. Right? Good answer again, Shaurya. 2, 3, 4 by 6. Remainders 1, 2, 3, 4, 5. How many integers from 1 to 100 belong to this set? 0. Okay. So the logic here is, if you're dividing by these numbers and you want remainders as these, then you can see difference between each divisor and its corresponding remainder is 1, right? So 2 minus 1 is 1, 3 minus 2 is 1, right? All of them you get a common difference as 1. So answer will be LCM minus 1, right? And LCM of these numbers is 60, right? So it will be either 60 minus 1 or a multiple of 60, let's say 60x minus 1. So how many integers between 0 and 100 belong to this set A? You can see, if you put x is equal to 1, then you will get 59. You can even verify whether this number satisfies all conditions or not, right? So indeed, this is the only number, because if I put x equal to 2, the other number you'll get is 119, and that's clearly not lying between 0 and 100. I'm quite surprised that you got this one wrong, sorry. Right? It includes the, the same concept of counting that we learned in the last class, right? You're counting multiples of 60 that lie in that range, and then you'll check whether one less than those multiples of 60 will also work, and that's that's what tells you the answer. Okay, here's question number 9. Find the largest 4-digit number that when divided by 6, 15 and 35 gives remainder of 12, 11 and 31 respectively. Let you think about this. Again, no options, precisely because I want us to understand the basic concept, right? Surely with options we can do much faster. Let's see. Right, so you want the largest 4-digit number that when divided by these gives, is there a pattern? 6 minus 2 is 4, 15 minus 11 is also 4, and 35 minus 31 is also 4. So basically it will be LCM into some value n minus this common difference of 4. That's what all numbers will look like. Okay. Right, so let me say LCM into x, right? What is the LCM of these numbers? 6 and 15 have LCM of 30, and 30 and 35. 30 is 6 into 5, and 35 is 7 into 5. 5 is common, 7 and 6 have LCM of 42. So LCM will be 42 into 5, that's 210. So it will be a multiple of 200 minus 4. Yep. So 210 minus, multiple of 210 minus 4 is the number that you have in mind. You want this to be as large a 4-digit number as possible. The largest 4-digit number is 9999. How close can you get, right? So 210. Let's just divide 9999 by 210. That's something which is pretty easy to do. right? So let's go ahead and do that, right? Divide this by 210. 210 into 2 into 4 is 840, right? That leaves me with 1599, and 210 into 7 will give me 1470, right? That gives me a remainder. I don't care what the remainder is. I know it's 129, less than 210, right? And so the 47th multiple of 210 is going to be slightly less than 9999. So this 47th multiple minus 4 will give me the answer. So n should be 210 into 47 minus 4, right? What is this? So it's going to be 129 less than 9999, right? So that's going to be 9870 minus 4 will give me 9866. Good answer, Shaurya. Alright, here's another one. This is a tricky one, right? But I'm going to ask you nonetheless. See if you can figure it out. It's a little maybe out of scope even, right? But since we are on this topic, there's no harm in quickly sort of discussing this. Right? Forget that you want the largest 3-digit number for first. You want a number which when divided by 7 gives a remainder of 2. So basically a multiple of 7 plus 2, right? But it should also be giving a remainder of 7 when divided by 8, which means it should also be, so instead of putting q, I'm going to choose different constants. I'm going to say, let's say it's the 8th multiple of 7 plus 2. It could also be 8b plus 7. Remember, dividend equal to divisor into quotient plus the remainder. So we are assuming that a and b are the quotients. Right? So now to calculate the value of n, first of all, right, in order to combine these two statements, you'll do a little bit of trickery. This is the kind of trickery I'm talking about, right? So write 7a as 8b plus 5. Right? Write it like this. Right? And then you think, okay, can I rewrite this to bring 5 inside a bracket, right? So for example, so here what I can do is I can write this as 8 times b okay, let's say I do minus 2. So since I'm writing it as b minus 2, I'm getting 8b minus 16. So I'll add the 16 back, right? And then obviously there was a 5 to begin with, right? So 16 plus 5 becomes 21. Bring that here. So 7a minus 21 is equal to 8 times b minus 2, which basically means that 7 times a minus 3 is equal to 8 times b minus 2, right? So this becomes, so this representation is that somehow this represents a multiple of 7, that's also a multiple of 8, and since it's a multiple of 7 and 8, it must be a multiple of their LCM, right? So this number will be a multiple of their LCM, right? But more importantly, a minus 3, right? Since this number is a multiple of 8, it cannot be 7, so clearly a minus 3 can be written as a multiple of 8, let's say 8c, which immediately gives me the value of a as 8c plus 3. And if you substitute this in the original expression here, you will get n as 7 times 8c plus 3 plus 2. Right? So that gives me 56c plus 21 plus 2, 23. Right? So this is a generic expression that we've derived. Right? All numbers in this expression will give me, a remainder of 2 when divided by 7. So for example, put c as 0. You'll get n as 23. If you put c as 1, you'll get n as 89. And you can check with these numbers. 23 divide by 7, remainder 2. Divide by 8, remainder 7. About 89 divide by 7, remainder is it right? No, this is 79. Sorry. Right. So 79, remainder 2, and divided by 8, 8 9s are 72, remainder is indeed 7, right? So all numbers of this form. Now you want to go and obtain the largest such 3-digit number. So if you want the biggest such 3-digit number, you want 56 into something to be as close as possible to 999, right? So we go ahead and divide 999 by 56. 56 ones are 56. That leaves me with 43. So 439, and 56 into, if I try 8, it won't work. So I'll have to try 7th multiple, right? So 17 into, so you'll have to put c as 17. So n becomes 56 into 17 plus the 23. Let's see if it falls inside. Is it a 3-digit number or not? 3-digit number or not? 17 into 6 is 102. 10, 17 into 5 is 85 plus 10, 95. So 952 plus 23 is 975. Right? So that's option B, right? I mean, obviously in this case you didn't have to do all of this. You could have just divided, right? You could have just avoided all of this and divided, but I've just, just in case I showed you the approach, right? It's a really hard, way of solving questions. So just sort of make note of it. Good answer, Asim. Yeah. Okay. Here's part 2 in today's session, right? So up until now, what we were doing is like basic, right? Most of the questions up until now, you can expect such questions in the GMAT also, right? But then going ahead, the questions that we'll get are rare questions, which means they're going to be 700 plus level questions if they indeed feature at all in the exam, right? So let's start with this. First of all, talk about factorization, right? So you can take any number and you can prime factorize it, which means you can write it as a power p, b power q, c power r, etc., where a, b and c are the primes and p, q and r are their powers, right? But if I gave you a number of this form and I asked you to count the total number of factors in n, how many factors does n have? If you can prime factorize and give me a form, right? Can I determine the number of prime factors? Sorry, can I determine the total number of factors? Well, the answer is yes, right? And the way that you derive it is that you should think that any factor that you want will itself be created by multiplying a power of a with a power of b with a power of c, right? So you will basically raise a to any power, let's say 0, 1, 2, 3, etc. You cannot exceed p, right? So a power 0, a power 1, a power 2, any of these values can be included all the way till a power p. So how many such possibilities have you generated? You generated p plus 1 possibilities, right? Okay. So you will choose one of these p plus 1 possibilities. Similarly, you will choose one of the p plus q plus 1 possibilities out of b, and you will choose one of the r plus 1 possibilities out of powers of c, and so you will get the total possible products will give me the total factors, which would be p plus 1 into q plus 1 into r plus 1 and so on, right? So while the derivation is not that important, I think what you need to keep in mind is that if you prime factorize, right, and the powers are p, q and r, right, I don't care about the primes, right? If their powers, power of every prime are p, q, r, etc., then you take those powers, increment there by 1 and then multiply all these numbers. That will give you the total number of factors that n has, right? Right. So this was to count the number of factors, but there's one other thing you can do. For a number in this prime factorized form, you can also recreate an expression that looks like this. Look at this carefully. What have I done? Where we counted in the previous case, we counted all possible powers of A, all possible powers of B, all possible powers of C. In this case, I'm putting all those powers as sums in different brackets. So 3 primes means 3 brackets, right? And each bracket will have powers, all possible powers of A, all possible powers of B, all possible powers of C. And if you multiply these, what do you get? Every product here will be a prime factor. Sorry, will be a factor, right? If, for example, if you multiply this, this and this, you will get 1. That's a factor. If you multiply this, this and this, that's another factor. What is that factor? A, C square, B square, C square. So you can get many such factors by simply multiplying a term from each of the 3 brackets. So the total number of products you will get will be P plus 1 into Q plus 1 into R plus 1. That's the number of factors. But if you evaluate this expression, won't you get all factors written one after the other and then getting added, right? Which means you'll get the sum of all the factors, right? So if I give you a prime factorized form, A power P, B power Q, C power R, then you can tell me 2 things, right? P plus 1 into Q plus 1 into R plus 1 will be the number of factors it has. And this expression, all powers of A from 0 to P, all powers of B from 0 to Q, all powers of C from 0 to R, separately added in 3 different brackets and multiplied will give me the sum of all the factors in the number n, right? And in fact, this expression does indeed also tell me the number of factors, right? Which is P plus 1, Q plus 1, R plus 1, right? Okay, and so, right, consider an example before we move ahead. Let's say I have a number, let's say 120, right? And I want how many factors does 120 have? So first thing I'll do is I'll write this in the prime factorized form. What's the prime factorized form? This is 2 cube into 3 into 5, right? 15 into 8 is 120. 2 cube into 3 into 5. What are the powers? 3, 1 and 1. So if I want the number of factors, right, that's going to be 3 plus 1 into 1 plus 1 into 1 plus 1. What is that? 3 plus 1, 4. 4 into 2, 8. 8 into 2, 16. So there will be 16 factors, right? And if I wanted the sum of all the factors, then first bracket put 1, 2, 2 square, 2 cube. Second bracket puts 1 and 3, and third bracket put 1 and 5, right? So what do you get? 1 plus 2, 3, 3 plus 4, 7, 7 plus 8, 15 into 4 into 6, right? 15 into 4 is 60, 60 into 6 is 360. So what this tells you that there are 16 factors. If you add all the factors, 16 factors, you'll get a sum of 360, right? And I hope that makes sense, Shaurya. Just let me know in the chat, Shaurya, Naseem. Right? Just give me a thumbs up in the chat if that makes sense to you. I'll understand from there, right? All right. So this was the approach to count the number of factors as well as sum of factors. Should be a slightly complicated question if you're getting this, but you can also comment and calculate either the number of factors or sum of factors when they are odd or even when they are multiples of other numbers, right? And that's also possible. Let's consider an example, right? So if you have A power P into B power Q into C power R, you have this expression to get the number of factors, right? Okay, so if I want you to tell me, will the number of factors be odd or will the number have an even number of factors, right? You remember in the previous example that we took, 120 had 16 factors, so it has an even number of factors. So the question here is, if I look at this expression for the number of factors, can I deduce something which tells me that the number of factors are odd in number or even in number, right? Can I tell that? So first question we should ask ourselves is, when will this, when will the number of factors be odd, right? Which means, when is this product odd? So remember, a product is odd only if all the numbers are odd, right? Each of these brackets should be odd in value, right? Which means P plus 1 is odd if P is odd, right? Q plus 1 will be odd if Q is even. R plus 1 is odd if R is even, right? So what that tells me is that each of these powers P, Q and R would be even in value. And what happens if the powers, right? All primes have even powers, then the number is called a perfect square, right? In effect, you can comment that it's a number will have an odd number of factors only if it is a perfect square. If it's not a perfect square, it will have an even number of factors, right? It's as simple as that, right? So besides counting the number of factors and sum of factors, you can also comment whether a number has odd number of factors or an even number of factors. Yeah. All right. So there you go. That's something that you can derive from here, right? Let's look at some questions based on this principle, right? Simple questions first. How many possible divisors can divide this number n? 2 power 4 into 5 power 4 into 7 power 3. And this is going to be a cakewalk because you want how many possible divisors. Divisors translates into factors. You want the number of factors. So number of factors will be 4 plus 1 5 into 4 plus 1 5 into 3 plus 1 4. That's 25 into 4, 100. So this number should have 100 factors. Right? Okay, let's move on, right? I'm going to ask you to solve this question, right? It's a slightly different question. Don't use the, the sum of factors or number of factors logic here, right? Just try and answer this with an open mind. If a number n is written as 2 power 4 into 3 power 2 into 5 power 4, how many unique unordered pairs a comma b can be created such that a into b is equal to n? Right? How many a comma b pairs can you create? Don't order them, but you must create them so that a into b is equal to n. How does this relate to what we just learned, right? Counting the number of factors and the sum of factors, right? Will that come into play when we're trying to count pairs of factors whose product is n? See if you have any thoughts on this. Okay, I can see one answer. Wonder if I need to give you more time. Two or three? No. Okay, so here's the logic, right? Now, let me, in such questions, by the way, there's a quicker way of doing it. First of all, you should notice that n is a perfect square, right? Did you notice that? Powers are even, right? So it's a perfect square, right? So let's do one thing. Let's consider a perfect square. No, let's say 64, or let's take another value, let's say 36, right? So 36 can be written as 1 into 36, or 2 into 18, 3 into 12, 4 into 9, and finally 6 into 6, right? So how many pairs? I'm getting 5 such pairs. Yeah. But how do I get this value? Obviously, if the number is much larger, right? Okay, so the logic is that if you look at prime factorized form of 36, what is this? 9 into 4, right? So 2 square into 3 square, right? So the first thing you'll notice that the number of factors that 36 has is 3 into 3, right? 2 plus 1 into 2 plus 1. So it has 9 factors, right? So if you have 9 factors, right, for every factor you will have one other factor which will be its pair, correct? Which means if you have a total of 9 factors, ideally if you pair them, you'll get 4 pairs and then one factor will be left over. And why do I have one factor left over? Well, because the number is a perfect square, which means there will be one pair where the square root is paired with the square root, right? So divide by 2 and then add 1 to it. That's your answer, right? So I can do that here also, right? How many factors does it have? The number of factors of n would be, increment the powers by 1, 4 plus 1 5, 2 plus 1 3, 4 plus 1 5. This gives me 75 factors, right? So if this number has 75 factors, how many unique pairs will I get, right? So 75 divided by 2, the absolute value I'll get will be 37. So 37 unique pairs, right? Unique, by unique I mean pairs where A and B are both distinct, right? So instead of saying unique, maybe you call them distinct pairs. How many distinct pairs do I have? 37. But how many total pairs? Because it doesn't say it needs to be distinct, right? So total number of pairs would be one more than this. That's going to be 38. That's your answer. Yeah, does that make sense, Asim? Good answer, Shaurya. Good answer. Right? So if you want the number of such pairs, count the total number of factors. If the number of factors is odd, well, then halve it and then add 1 to it. If the number of factors is even, just simply halve it. That would be your answer. Alright, here's another question. If n is the integer, how many values of n will give me integer values to this? Are you overthinking this? You want this expression to be integral, right? What if you divide this? Split this, 16n plus 7 plus 6 by n, which means this is integral if 6 by n is integer, right? And when is 6 by n an integer? If n is a factor of 6. Right? How many values can n take? Well, 1, 2, 3 and 6. 4 values. Answer 4. Easier than you thought, right? Certainly hope it felt that way. It's a very, convoluted way of saying count the number of factors that 6 has. Hope that you saw that. Alright, here's no Asin, that was 4 values. N can take 4 values. Here's question number 14. P is given to me as 648 and Q is given to me as 972. Find the number of factors of P that are also factors of Q. Basically find the number of common factors. Oh, okay, 15. Right. So the idea here, if you haven't figured it out yet, right? I told you common factors, right? So you want common factors between P and Q. So all common factors of P and Q will also be factors of their HCF. So the first thing you'll do is you'll try and prime factorize and calculate their HCF. So I can write this as 6 into, what is this, 108, 12 into 9, or 27 into 4, right? So this becomes 3 power 4, 81 into 2 power 3, that's 8, and Q will in fact be 972, that's 9 into 108. Right, and I think I see where this is heading. Clearly the HCF will be 108. Right, you can see. You can, from factorizing itself, you can see. So HCF of the two numbers is 108, which is HCF itself is 2 square into 3Q. Sorry, 2 square into 3Q. Right. So HCF has how many factors? So how many factors does this HCF have? That's going to be 2 plus 1, 3. into 3 plus 1 4, so I'm going to get 12 possible such values, which will be factors of P and also factors of Q, right? Common factors, all factors of their HCF. Does that make sense? No, wait, I think I made a mistake here. Yeah, HCF is not 108. HCF is not 108. In fact, because 108 is common to both numbers, but then 6 and 9 also have 3 in common, right? So HCF will be 108 into 3. So that's like 3 power 4 into 2 square, right? HCF is 2 square into 3 power 4, right? 81 into 4, there are 324, right? So the number of factors will be 2 plus 1 3 into 4 plus 1 5. So yes, HCF will have 15 factors, so there will be 15 factors of P that are also factors of Q. Good answer, Shaurya. Pat on back, man. And obviously this one is easy. Find the sum of all the factors of 120. I know we have already done this, right? We already got 360 as the answer for this. So I'm going to skip this question. Move on to the next one. Find the sum of all even factors of 180. How do I get there? Yeah, last 15 minutes. Quickly discuss some. I think these are out of scope for the GMAT. But then again, it's not very hard. Once you know how to count factors, it's not very hard to count the sum of all the even factors of 180. Remember, 180 can be written as 36 into 5. So that 36 is 2 square into 3 square and so into 5. Okay. So you have the prime factorized form for 180. You want the sum of all even factors. Right? But you can start with this expression. What is the sum of all the factors? 1 plus 2 square. Write all the powers of 2. Next bracket all powers of 3. Then next bracket all powers of 5. Yes. So I get this expression. But you don't want. This will give me sum of all factors. You want the sum of only even factors. So this doesn't help, right? So what do you do? And in fact, forget this expression for now. How do you calculate the sum of only the even factors, right? So you'll use this definition. Let's say n is an even factor. What will n look like? 2 times something. N will be of the form. It has to contain a 2, right? So it will be 2 into something, 2x, right? And if n is a factor of 180, then n into something, b, should be equal to 180, right? N into b ki jagah let's take y. So if n is a factor, n into something else should give me 180, and so I write that expression, right? And now if I substitute the value of n from the previous expression for n as 2x, so 2x into y gives me 180, which means x into y should be 90. Okay, this gives me something interesting. What does this mean? This means x is a factor of 90. Okay, x is a factor of 90. How many factors does 90 have? 90 itself is 2 into 3 square. 2 into 9 is 18. 18 into 5 is 90. So 90 can be written as 2 into 3 square into 5. So if x is a factor, x can take how many values? 1 plus 1 2, 2 plus 1 3, and 1 plus 1 2. So 2 2s are 4, 3s are 12. So x can take 12 values. And if x can take 12 values, 2x will also correspondingly take 12 values. And each of those values will give me a factor of, okay, this was actually the okay, come back to you, Asim. But for now, right? Sorry, this was an approach to calculate the number of such even factors. You'll have 12 such even factors is the answer, right? But instead, if you want the sum of all these factors, right? So you'll basically want, let's say x1, x2, x3, etc. are, right? 2x1, 2x2, 2x3, etc. are those values, right? So you want 2 times You know, if I can take 2 common, I'll get 2 times x1 plus x2 plus x3. How many such factors? 12 factors. You want sum of 12 factors. But what is this bracket? Sum of all possible values of x, right? Which means sum of all these 12 values, which means sum of all these 12 factors of 24, of 90, sorry. So 2 into sum of factors of sum of all the factors of 90. But I know how to write an expression for sum of factors, right? Right? Simply go with the prime factorized form and write corresponding terms for each power of, you know, the prime. 1 plus 2, for 3 square I'll write 1 plus 3 square, and for 5 I'll write 1 plus 5, right? So what is my answer? 2 into 3, 6. This is 3 plus 1, 4. 9 plus 4 is 13, and that is 6 again, right? So 13 into 36, the answer I'll get is 13 6 are 78, 13 3s are 39, 39 plus 7 is 46. So 468, the double of 234, 468 is the sum of all the factors of, all the even factors of 180. Does that make sense, Shaurya and Aseem? I just put in a word in the chat so I know that it's clear to you. Yeah, let me recap, right? Let me recap again, right? So what you'll do is you'll say even factor means 2x, and if it's a factor, 2x into y should be 180, which means x into y is 90, right? So if you want sum of all factors of 100 and sum of even factors of 180, right, this will be 2 times the sum of factors of 90, right? So 2 times, and then you create that expression, right? 90 itself is 2 into 3 square into 5. So 1 plus 2, 1 plus 3 square, and 1 plus 5. And if you calculate this, you'll get the answer as 468. Super. Here's the next question. Find the sum of all factors of 1260 that are also divisible by 30. So basically you'll say, how is it different from the previous one? You still want sum of factors, but now you want factors of 1260 that are divisible by 30. So if a factor is divisible by 30, you'll say the factor will be of the form 30x, right? And if it's a factor, then 30x into y should be 1260, which means x into y would be, how much is this? 3 4s are 12, 3 2s are 6. So x into y will be 42. So x will be all factors of 42. So sum of all values of x will be sum of all factors of 42. So the answer here will be, 30 times sum of all values, sum of 30 times sum of all the values of x, which means 30 times sum of factors of 42, right? 42 itself is 7 into 6, right? 2 into 3 into 7. So 30 times 1 plus 2 into 1 plus 3 into 1 plus 7, right? What does it mean? What do you get? That's 30 times 3 into 4 into 8, right? 12 into 8 is 96. 96 into 30, right? That's going to be, how much is this? 2880. Does that make sense? We've already done the 18th one, so I'm going to skip and discuss question number 19. Let me give you a minute to quickly try this yourself. Right, let's look at this one. Right, the question says how many divisors of p square. First of all, how many factors? Right, divisors and factors are interchangeable words. How many factors of p square? So what is p square? P itself, needs to be prime factorized. So that's 3 into 5, right? So 3 power 8 into 5 power 8, and this is 2 square into 5, 4 into 5. So 2 square means 2 power 10, and into 5 means 5 power 5. So what does this become? 2 power 10 into 3 power 8 into 5 power 13. So p square will be 2 power 20 into 3 power 16 into 5 power 26, right? And the question says how many factors of p square are less than p and do not divide p, right? Which means are not, if a number doesn't divide p, it's not a factor of p, right? Are not factors of. How do you calculate this? First of all, how many divisors of p square are less than p, right? The trick is to remember, you remember those pairs that we learned how to count. Total number of pairs will be number of factors divided by 2, right? But the reason why those pairs are useful is also in this case, right? Because in every pair, if you remember, in every pair, one factor will be less than the square root and one factor will be more than the square root. It has to happen that way, right? So the total number of distinct pairs will contain all factors of p square that will be less than p, right? So the first statement is first thing you should do is count the number of distinct pairs, because each pair will give me one factor which is less than p, right? So you'll get the number of distinct pairs, but from this you need to also subtract all factors of p, right? But then there is a problem, right? Because distinct pairs will only contain factors that are less than p, but factors of p will contain, besides containing factors that are less than p, it will also contain one factor which is equal to p, right? Which means you'll subtract one more number than you actually should, so add back that one number, right? So my answer is calculate the number of distinct pairs. How do I get the number of distinct pairs? Total factors, that's 20 plus 1, 21 into 16 plus 1, 17 into 26 plus 1, 27. Distinct pairs will be this minus 1 divided by 2, or just divided by 2 and ignore the decimal. And from this subtract all factors of p. Factors of p will be 10 plus 1, 11, 8 plus 1, 9 and 13 plus 1, 14. But don't exclude all the factors of p, because one factor wasn't even counted here, which was the number p itself. So since that wasn't counted, add it back. Right? So how much is the answer? Okay, this is a difficult calculation. 21 into 7, 147. 21 into 2, 42 plus 14, 56 into 17, right? Minus 1. So what do I get? 17 7 is 119. 17 6 is 102 plus 1, 113. 11 again. 17 5 is 85. 85 plus 11 is 96. So 9639 minus 1 divided by 2 minus, what is this number? Right? 99. So 11 into 14 is 154 into 9. So 9 4s are 36. 9 5s are 45 plus 3 48. 9 1 are 9 plus 4 13. So minus 1386 plus 1. So my answer becomes, how much is this? 9638 divided by 2 minus 1385. What do I get? That's 4819 minus 1385. 9 minus 5 is 4. 11 minus 8 is 3. 7 minus 3 is 4 and 3. Right? So 3434, which indeed is none of these options. Option D, I think, which is what Asim told me. Right? So it's a tough question. I hope it makes sense to the two of you. Right? So count the number of factors, total number of factors that p square has. From the total number of factors, count the number of unique pairs, distinct pairs. Right? So subtract and divide by 2, or divide by 2 and ignore the decimal part. So that gives me the number of pairs. Since every pair contains one factor that's less than the square root, this will give me the number of factors that are less than p. From those you need to exclude all factors of p that are less than itself, right? So one less. Subtract that value and you'll get the answer. Right? There is one more question, right, in today's exercise, which is that if J is a natural number, J is a natural number which has exactly 4 factors, right? J is a natural number that has 4 factors. How many such numbers can exist such that J is less than 100, right? Okay, think about it. J has 4 factors, right? If I write J as a power p into b power q, where a and b are the primes, then the number of factors it will have will be, the number of factors would be p plus 1 into q plus 1 into r plus 1 and so on, which is given to me as 4, right? So I can write 4 either as 1 into 4 or as 2 into 2, right? Two ways of writing this. What do each of these representation mean, right? 1 into 4 means 1 is useless, right? 0 plus 1 is 0, right? Which means there is one factor, right, which is cubed, right? Basically J is of the form a cube, right? How many factors will it have? 3 plus 1, 4, right? Or if it's 2 into 2, then it has 2 factors which have power as 1 with power equal to 1, right? What does that mean? So for example, J can be of the form a power 1 into b power 1, in which case your number of factors you'll get is 1 plus 1 2 into 1 plus 1 2, that would be 4. So two possible expressions: either a number is whole cube of a prime number, or it's the product of 2 primes, right? So let's calculate this separately, right? How many cubes do you have? So 2 cube is 8, yes. 3 cube is 27, yes. Next number is 5. 5 cube is 125, that doesn't count. So only 2 such values. Okay. How about A into B, right? How about products, right? So what I'll do is I'm going to start counting, right? With 2, how many pairs can I make, right? With 2 I can make 2 comma 3, 2 comma 5, 2 comma 7, right? So instead of writing it this way, which will take a lot of time, right? Why make so many pairs, right? Let's just represent that as, with 2 you'll get 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43 and 47, right? Essentially all factors till 50, you know that there are 15 factors till 50, right? And so if you exclude the number 2 itself, you'll get 14 other factors, which means these 14 factors can be paired with 2, so you'll get 14 such values of J, right? 2 into 3, 2 into 5, 2 into 7 and so on, right? Then instead of 2, what if you multiply something with 3, right? So what else could you multiply? 5, 7, 11, 13, 17, 3, 19, right? You can go till 33, remember. 19, 23, 29 and 31. How many pairs? 1, 2, 3, 4, 5, 6, 7, 8, 9, which means 9 values, right? Similarly, pairing with 5, you can pair with 7, 11, 13, 17 and 19, which means 5 such values. With 7, pair it with 11, 13, maybe even 17, no, 17 into 7 is 119, so 2 values. Right? Can I pair something with 11? No, 11 cannot be paired, right? So that's it. Total how many values? 2 plus 5, 7 plus 2, 9, right? 9 plus 14, 14 plus 9 is 23, 23 plus 9 is 32. So answer is option C. There are 32 such sessions. Well, Asim, I don't think I have a YouTube session on mixtures and alligation. You'll have to find that in special classes. Unfortunately, not available on YouTube. Right? Well, I hope you guys had fun. I hope it wasn't too challenging. But like I said, I think some of these things are just too hard. Don't expect to get it on the GMAT. Maybe in the off chance that you get, I did teach you, right? But it looks highly unlikely. 3 good reasons to join Unacademy. That's what I'm going to leave you with. 1, flexibility. You get plenty of flexibility. You can choose on any, you can choose to learn on any device, you can choose to learn any time of the day, choose a schedule that works for you, right? In fact, learn in multiple languages also, right? Regional languages included. So flexibility. Two, the second big advantage is interactive, right? It's an extremely interactive platform. You can interact with the educator, you can ask doubts, you can ask questions. The educator can pull your doubts on the screen as the class is going on. Pull your doubts on the screen, solve it then and there, right? That can happen. And you can also answer quizzes and live polls, right? So very, very interactive, two ways. And finally, plenty of practice, right? There's plenty of practice to do. You can practice live tests, you can practice, and look at your reports and performance analysis. You can even download your PDFs, right? Whatever I teach, if it is on Plus platform, then you can even download the PDFs. All you need is a valid subscription plan. I'll leave you with two words of advice. One, if you enroll, choose the longer term plans, right? And remember to use the referral code AV01 because this gives you a 10% discount. Straight away, you get a 10% discount on using AV01. So keep that in mind. If you like this session, do like, share, and subscribe to this channel. Do share it widely. This is where I say goodbye to all of you. Asim, he must have downloaded from YouTube. Unfortunately, this is not my domain. This is Unacademy's domain. If the video has been unlisted, I can't really do much about it, man. I did look for it, I couldn't find it. Yeah, so just search for it on special classes. Maybe you'll find it there. Okay. On that note, thanks a lot, guys. Have a great day. I'll see you guys very, very soon. I think Tuesday. Same time, 7 p.m. on Tuesday is when we meet again. We'll have a crack at another topic relevant to the GMAT exam or most other Indian exams.